All right, next we have 7.3, which is trigonometric substitution, which is a really neat way of, uh, it's a really neat substitution technique. So essentially, what you are familiar with so far with U substitution is letting a new variable, U, equal some part of an existing expression in our integrand. So for instance, if we had something like e to the x over e to the x plus 1 dx, we could let u equal e to the x plus 1, the entire denominator, and then this substitution here would change this integral into the integral of 1 over u du. This new technique that we're going to do is, instead of letting a new variable equal a part of our existing expression, we are going to take our current variable, and set it equal to some expression, specifically one that involves a trig function. No matter how you chalk it up or how differently you think of U substitution and this trigonometric substitution, they are still substitution methods, so they really are one and the same. It's just that this is a very specific sort of set of functions that we will be substituting in. And so they have different algebraic circumstances. They will arise when you have certain algebraic expressions in your integral. Okay. So let's take a look here in this introduction. Essentially, we're going to start by looking at expressions that have square roots in them. You can use trig sub for an expression even when you don't have any sort of square root. That's not required. But there is this identity, a set of identities that we're going to exploit, and they do come in the form of squares. We have the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, or tangent squared theta plus 1 equals secant squared theta. All of these identities, these Pythagorean trigonometric identities, they have to do with squares. So whenever you've got a square root or squares showing up, trig sub is going to be a natural thing to use. So yeah. Another way to think about this, a motivating example or a motivating perspective, is many of the integrals that we're going to look at have expressions like this in them. So for instance, if I have the integral of the square root of, let's say, 4 minus x squared dx. Well, the issue here is, hopefully you've learned this already from Calc 1, and that is, if you have an integral coupled with a square root, usually you're in for a rough ride. Not always, but immediately it's most likely going to be a U substitution. So square roots and integrals usually means a tricky integral. It would be nice if the inside of our square root were a perfect square. For instance, if I had the integral of the square root of, let's say, x squared plus 6x plus 9 dx, that wouldn't be that bad, because the inside is really a perfect square. It's x plus 3 quantity squared, in which case I can go ahead and say that is the integral of this. And if I happen to know that x is, I don't know, bigger than -3, then, so for instance, if I were doing some definite integral, let's say, from 0 to 1, then I wouldn't even need the absolute value bars. So very nice to do. But unfortunately, these expressions of these forms here, they are not perfect squares. So the neat thing about trigonometric substitution is that you take something that, as written, beginning with. It's not a perfect square, but when you perform this substitution, it turns into a perfect square. So for instance, the appropriate substitution for this kind of integral would be let x equal 2 sine theta. Then dx is 2 cosine theta. So then this integral here turns into the square root of 4 minus 4 sine squared theta. And dx is 2 cosine theta d theta. I forgot my theta, or my d theta. And then using the Pythagorean identity, this is none other than 4 cosine squared theta, which is a perfect square. So we have 2. Actually, let's write it this way. This is the integral of 2 cosine theta times another 2 cosine theta d theta. So this is 4 cosine squared theta d theta. And then from here, we can use the half angle identity to integrate this readily. So that's the magic right here, is this substitution together with the identity changes this into a perfect square, in which case the square root gets removed. So that's the utility, okay? Okay. So we've got some forms here. And the reason why we have these different forms is, well, for the minus signs, we've got an order of subtraction. If you subtract them in the one order, it's different than subtracting in the other order. And then here, the plus sign, there's no variation because the order doesn't matter when you're adding positive things. Okay, so the reason why we have these forms in particular is they match and line up with our main identities. So the one identity here is, of course, we have sine squared theta plus cosine squared theta equals 1. So we can think of this as, let's go ahead, instead of sine squared theta plus cosine squared equals 1, let's multiply by a squared, some constant. Then a squared minus a squared sine squared theta equals a squared cosine squared theta. So you can see that if our original term is a squared minus x squared, you would let this be the x squared. So this identity lines up with this format here. These two identities have to do with the related trigonometric identity of, let's make this in black, tangent squared theta plus 1 equals the secant squared theta. Again, let's just multiply by some constant a squared to get things matching up nicely. And now that we have this, you can see that there's two options. The one option is, so option 1 is we have a squared tangent squared theta. Well, actually, it's as is. It's already done. So this is the one option right here. And this would line up with this format here. In which case, this right here would become our x squared. So x squared plus our a squared. And then if you rearrange this to solve for a tangent squared theta, so this would be a squared secant squared theta minus a squared. This equals a squared tangent squared theta. So here, this one, number 2, actually, let me label these 1, 2, and 3. There we go. That lines up with this one. Variable squared, right? If that's our x squared, so variable squared minus a squared equals that perfect square. So the reason why these forms are what they are is because we are algebraically exploiting the form of these identities, which these identities have their form based on the Pythagorean theorem and the definition of sine, cosine, tangent, secant, so on and so forth. Okay. So taking a look here at example 1, we just want to identify what the correct forms would be, what the correct substitution would be. So really, ideally, we want the coefficients here to match, right? If this is an a squared, so let's say this is 9, we want this to be a 3 sine theta, because when we square it, we want this 3 to match the 9. So down here, the correct substitution would be x equals 3 sine theta. Now you might ask yourself, wouldn't x equals 3 cosine also work because of the structure of this identity algebraically, right? I chose to subtract the sine over to the other side. Couldn't have we subtracted the cosine over and put the sine back? Absolutely. Cosine does work as well. There's a reason, though, why we don't choose x equals cosine theta, and it's sort of a petty reason, and it's because when you go to find your differential, which is the very next step, you get a negative. There's nothing wrong with a negative, but if you can choose two equally comparable effective substitutions, why would you pick the one that introduces this negative? That's just going to make it slightly more complicated. Sure, we trust that everyone knows how to handle a negative, but we can all agree that lots of double, triple, quadruple, whatever negative symbols floating around a problem can make it kind of annoying or difficult at times unless you simplify them. So if we can avoid introducing these unnecessary negatives, then that's a good thing. So that's why you'll never see cosine used. Okay, so x equals 3 sine theta. And you can see what will happen here is that the inside of the square root becomes 9 minus 9 sine squared theta, and then the Pythagorean identity makes this 9 cosine squared theta. So that's what we get. We get a perfect square. Okay, this one here is a little bit trickier to see, but again, just think about the inside of the fractional exponent, the thing that has the format, something squared plus or minus something else squared. In this case, we would let x equal, well, it's going to be 4, but then the order of this subtraction is going to be secant theta. And then this will make this 3/2 term turn into an 16 secant squared theta minus 16, which is a 16 tangent squared theta to the 3/2. And then it's a perfect square, so that works out. Here, we're going to have x equals 4 tangent theta. Down here, we will have, so 5 is not a perfect square, right? It's not a whole number. It's not it's not an integer or something like that, but we can still just take a square root. So square root of 5, secant theta. Down here, this one's a little bit trickier. This would actually be 9, not 9, this would be 3/2 tangent theta. So this one is useful to see. This would be, right, 4, and then this would be 9/4 tangent squared theta plus 9. The fact that the 2 is in the denominator here, when we square it, it will be a 1/4, and then it will cancel that fourth. And then the 3 that was in the numerator, it gets squared, becoming a 9, and then we get the matching coefficients. So that one's takes a little bit more to see, but nevertheless, we get exactly what we're looking for.